Hey guys, tonight we look up at the night sky and feel something both humbling and vast. Above us, the stars burn silently, scattered across the dark canvas, while our own world drifts through this immensity like a single grain of sand caught in a cosmic tide. It's easy to forget that Earth, our home, every memory and story we've ever known, is just one planet among countless others. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me in the comments, where are you watching from, and what time is it right now? Earth's place in the cosmos. At first glance, Earth feels like the center of everything. The ground beneath our feet is steady, the sky arches overhead, and for most of human history, it only made sense to believe that everything revolved around us. Ancient civilizations, from the Babylonians to the Greeks, built elaborate models of the heavens, imagining Earth as the fixed hub of the universe. It was a comforting thought, one that aligned with our daily experience. But here's where it gets interesting. The deeper we looked, the more that illusion unraveled. In the 16th century, Nicolaus Copernicus dared to suggest that the sun, not Earth, was at the center of the system. His model wasn't perfect, but it cracked open the door to a revolution in human thought. Galileo, peering through his telescope decades later, saw moons orbiting Jupiter, a direct challenge to the idea that everything must circle us. Step by step, we learned that Earth wasn't the center at all, but just another world orbiting a star. Now let's place Earth in context. Our planet orbits the Sun at an average distance of 93 million miles, or about 150 million kilometers, a distance known as 1 astronomical unit. At this sweet spot, liquid water can exist on our surface, a key ingredient for life as we know it. The Sun is one of roughly 200 billion stars in the Milky Way galaxy, which itself is just one among perhaps 2 trillion galaxies in the observable universe. If you zoom out far enough, Earth shrinks to the faintest dot, smaller than a pixel. One of the most powerful reminders of this perspective came in 1990, when the Voyager 1 spacecraft, nearly 4 billion miles from home, turned its camera back toward Earth. The result was the famous pale blue dot photograph. Our planet suspended in a shaft of sunlight, almost invisible. Astronomer Carl Sagan described it as a mote of dust suspended in a sunbeam. In that image, every empire, every civilization, every joy and sorrow in human history rests on a speck of light. But let's not mistake smallness for insignificance. The very fact that we can step outside on a clear night, gaze upward, and wonder about our place, that's extraordinary. Our planet is more than just a location. It is a platform for consciousness, for awareness, for curiosity itself. From Earth, we've built instruments that can scan the universe's oldest light, map galaxies billions of light years away, and even detect ripples in space-time caused by colliding black holes. Think about this. The atoms in our bodies were forged in stars that lived and died long before the sun was born. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was created in the heart of ancient stars, scattered across space by colossal supernova explosions. When you consider this, Earth's place in the cosmos becomes not just a position in space, but part of an ongoing story of matter cycling through time. And yet, Earth is rare in its own way. So far, despite searching thousands of exoplanets, we haven't found another quite like it. That doesn't mean it doesn't exist. It almost certainly does, given the sheer scale of the universe, but it highlights just how special our circumstances are. A planet with liquid oceans, a protective atmosphere, a magnetic shield, and a stable orbit around a steady star. It's a fragile balance. The modern perspective shifts between two truths. On the one hand, Earth is cosmically small, a minor world in an unfathomably vast universe. On the other hand, it's the cradle of life, the only known place where the universe has become aware of itself. Both views are equally astonishing. To see why this matters, let's bring the focus closer again. Every sunrise and sunset, every ocean wave and mountain peak, every song and story, it all unfolds on this tiny sphere hurtling through space at nearly 67,000 miles per hour. Earth is not the center, but it is home, and that makes it remarkable. So when we ask, where is Earth in the cosmos? The answer is layered. It is one planet among billions, orbiting an ordinary star in the outskirts of an ordinary galaxy. But it is also the starting point of our exploration, the vantage point from which we've mapped the heavens, and the only world so far where the cosmos has opened its eyes. And as we continue this journey, chapter by chapter, keep this in mind: every star we study, every galaxy we glimpse, every mystery we unravel, all of it connects back to this small, pale dot, floating quietly in the dark sea of space. Our moon, silent guardian of the night. Here's a fact that might surprise you. Without the moon, life on Earth might never have flourished in the way it has. Night after night, it hovers above us like a constant companion, shaping not only our tides, but the very stability of our planet. Yet for something so familiar, the moon's story is filled with mystery, drama, and cosmic violence. To understand its origins, we need to go back about 4.5 billion years, to the chaotic infancy of the solar system. Back then, Earth itself was still forming, molten, unstable, constantly bombarded by asteroids. In this violent era, a Mars-sized protoplanet, often called Theia, collided with the young Earth in a catastrophic impact. The collision was so immense that it blasted molten rock into orbit, material that eventually coalesced into the moon we know today. This means the moon isn't just a satellite. It's a fragment of Earth's earliest history, a reminder of the chaos from which our planet emerged, and its influence has been profound ever since. Think about the tides. Twice a day, oceans swell and retreat because of the moon's gravitational pull. These tides have shaped coastlines, nurtured ecosystems, and may even have played a role in the origin of life itself. Some scientists suggest that shallow tidal pools, warmed by the sun, could have been the cradle where the first building blocks of biology assembled. But the moon does something even more vital. It stabilizes Earth's axial tilt. Without it, our planet's tilt could wobble chaotically over millions of years, leading to wild swings in climate. Imagine a world where ice ages and searing droughts arrive unpredictably, with no rhythm or stability for life to adapt to. The moon acts like a cosmic gyroscope, keeping Earth's orientation steady and seasons reliable. For ancient humans, the moon was more than science. It was story. Civilizations across the globe wove myths around its phases. To the Greeks, it was Selene, goddess of the night. To the Chinese, the moon was home to the jade rabbit, endlessly pounding the elixir of immortality. Farmers used its cycles to guide planting, while poets used it as a metaphor for longing and change. In every culture, the moon became a mirror for human imagination. Then came the space age. In 1969, when Neil Armstrong stepped onto the lunar surface, humanity achieved something almost unthinkable. We touched another world. The Apollo missions brought back rocks that told us more about the moon's geology than centuries of speculation ever could. We learned that the dark seas we see from Earth, the lunar Maria, are vast basalt plains formed by ancient volcanic eruptions. The brighter highlands are older, battered by billions of years of impacts. And perhaps the most humbling discovery of all, those Apollo astronauts looked back at Earth and saw it as a fragile blue marble against the vast blackness. That perspective changed how we think about our planet and ourselves. Today, the moon is far from forgotten. NASA's Artemis program aims to return astronauts to its surface, not just for exploration, but as a stepping stone toward Mars and beyond. Private companies dream of mining lunar resources. Ice and shadowed craters could be turned into drinking water, or even rocket fuel. The moon may become humanity's first outpost in the wider solar system. But despite all this, it remains what it has always been, a silent guardian of the night. It lights our skies, shapes our tides, steadies our planet, and stirs our imaginations. When you look up and see its pale glow, you are not just seeing a rock in space. You are looking at a relic of Earth's birth, a partner in our planet's journey, and perhaps a doorway to our cosmic future. So the next time the moon rises, take a moment to appreciate it. Our world would be unimaginably different without its steady presence. The sun, a gentle star at the center. To see why the sun matters, let's begin with something simple. Step outside on a clear day, close your eyes, and feel the warmth on your skin. That energy has traveled across 93 million miles of space, taking about 8 minutes to reach you. It is the same energy that fuels every tree, every breath of wind, every heartbeat on Earth. Without the sun, our planet would be a frozen wasteland, drifting silently through the void. Yet for all its power, the sun is, in astronomical terms, a fairly ordinary star, and that ordinariness is precisely what makes it so remarkable. The sun formed about 4.6 billion years ago from a giant cloud of gas and dust in the Milky Way. Gravity pulled this cloud together, compressing it until nuclear fusion ignited at its core. From that moment, hydrogen atoms began fusing into helium, releasing staggering amounts of energy in the process. This fusion has been ongoing ever since, turning the sun into a colossal engine, radiating light and heat in all directions. At first glance, the sun seems constant, always rising, always setting. But look closer, and you'll find a dynamic, restless star. Its surface, called the photosphere, is a roiling ocean of plasma where convection cells bubble and churn. Sunspots, dark patches caused by magnetic disturbances, appear and vanish in cycles lasting about 11 years. Massive eruptions, known as solar flares and coronal mass ejections, hurl charged particles into space, sometimes interfering with satellites and power grids here on Earth. The sun may seem gentle, but it is anything but quiet. Still, compared to other stars, the sun is stable. It is classified as a G-type main sequence star, or yellow dwarf, though in truth it glows white when viewed from space. Larger stars burn hotter and faster, often ending their lives in violent supernovae. Smaller stars, like red dwarfs, burn more slowly and dimly. The sun, by contrast, sits in a comfortable middle ground, large enough to provide ample energy, yet stable enough to shine steadily for billions of years. This balance has given Earth exactly the conditions needed for life to evolve and thrive. History shows how deeply humanity has depended on the sun. Ancient civilizations worshipped it as a god. The Egyptians revered Ra, the sun god who traveled across the sky each day. The Aztecs performed elaborate ceremonies to honor Tonatiuh, their solar deity, believing the sun needed human offerings to keep shining. Even in cultures without such personifications, the sun dictated life's rhythms: when to plant crops, when to harvest, when to prepare for winter. Long before we understood nuclear fusion, we knew instinctively that the sun was the source of life. But the sun isn't only about sustenance, it's also about perspective. Consider this. Our star is over 100 times wider than Earth, with a volume large enough to fit 1.3 million Earths inside it. Yet in the broader galaxy, it is utterly unremarkable. It is one among hundreds of billions of stars in the Milky Way, and the Milky Way itself is just one among billions of galaxies. That balance between grandeur and humility is part of what makes studying the sun so compelling. Think about the journey of a single photon, deep inside the sun's core, where temperatures soar to about 15 million degrees Celsius. Fusion reactions release energy in the form of gamma rays, but those photons don't travel straight to the surface. Instead, they bounce around for tens of thousands, perhaps even hundreds of thousands of years, colliding with particles in a chaotic random walk. By the time they finally emerge from the photosphere, their energy has transformed into visible light, the very light that illuminates our days. In a sense, the sunlight warming your face today began its journey long before the first humans ever walked the Earth. The sun's influence extends far beyond light and warmth. Its magnetic field creates a protective bubble around the solar system called the heliosphere. This shield deflects much of the cosmic radiation streaming in from deep space, protecting not only Earth but also the other planets. Without it, life might struggle to survive the constant bombardment of high-energy particles. Yet, like all stars, the sun has a finite lifespan. Right now, it is roughly halfway through its main sequence phase, with about 5 billion years of steady fusion left. Eventually, it will exhaust the hydrogen in its core. When that happens, the sun will swell into a red giant, engulfing Mercury and Venus, and possibly Earth itself. Its outer layers will drift away, creating a beautiful planetary nebula. What remains will be a dense white dwarf, a stellar ember slowly fading into darkness. For us, that distant future is both sobering and awe-inspiring. The very star that gave us life will one day consume us. And yet, this fate is not tragic. It's part of the cosmic cycle. Stars like the sun are factories of elements. The carbon, nitrogen, and oxygen that make up our bodies were once forged in earlier generations of stars, scattered across space when those stars died. In time, our sun will contribute its own material back to the galaxy, enriching the interstellar medium for new stars and planets to form. Modern science continues to probe the sun's secrets. Spacecraft like NASA's Parker Solar Probe are venturing closer than ever before, diving into the sun's corona to study its magnetic fields and solar winds. These missions don't just satisfy curiosity, they help us predict space weather, which can affect satellites, communications, and even the power grids that modern society depends on. In a very real sense, understanding the sun is as practical as it is profound. But beyond utility, the sun continues to inspire awe. Every sunrise reminds us of renewal, every sunset of passing beauty. Cultures may no longer worship the sun as a god, but in its light we still find meaning. It is both ordinary and extraordinary, a typical star, yet the most important one we will ever know. So the next time you look at the sun, remember this: you are not just seeing a glowing disk in the sky, you are witnessing a nuclear furnace that has burned for billions of years, whose light fuels every living thing on Earth, and whose story is woven into the fabric of our existence. The sun is not just at the center of the solar system, it is at the center of our lives. The solar system's hidden harmony. At first glance, the solar system looks like a jumble of planets, moons, asteroids, and comets, each moving in its own way. But beneath this apparent chaos lies a hidden harmony, a delicate balance of gravity and motion that has held together for billions of years. Like an orchestra where each instrument plays its part, the solar system operates through rhythms and resonances, mathematical relationships that give order to what might otherwise be disorder. To see this, let's start with the planets themselves. Each one follows an elliptical path around the sun, a motion first described by Johannes Kepler in the early 17th century. Kepler noticed that the planets do not move in perfect circles, as long believed, but in stretched ovals, with the sun at one focus. His laws of planetary motion revealed that the closer a planet is to the sun, the faster it moves. The farther away, the slower. This pattern is not random. It's the language of gravity, written across space. Isaac Newton later explained why this happens. His law of universal gravitation showed that every object in the universe attracts every other, with a force proportional to their masses and inversely proportional to the square of their distance. This simple principle is the thread that ties together everything from the orbit of the moon to the motion of distant comets. The solar system, it turns out, is not chaos, but choreography. One of the most fascinating examples of this hidden order is orbital resonance. Take Jupiter's moons, Io, Europa, and Ganymede. For every 4 orbits of Io, Europa completes 2, and Ganymede completes 1. This exact ratio locks them into a stable pattern, preventing collisions and maintaining their rhythms. Similar resonances exist among planets, such as Neptune and Pluto, which are locked in a 3:12 resonance. Though Pluto's orbit crosses Neptune's, the timing ensures they never collide. This harmony extends to gaps and patterns in unexpected places. The asteroid belt, for instance, is not evenly distributed. Instead, there are Kirkwood gaps, regions cleared out by resonances with Jupiter's gravity. Farther out, the rings of Saturn display intricate patterns, sculpted by the gravitational influence of its moons. Everywhere we look, we see the fingerprints of gravity, arranging matter into order. But harmony is not the same as stillness. The solar system is a dynamic, evolving system, shaped by both stability and disruption. Early in its history, giant collisions rearranged the architecture. Some scientists believe that Jupiter and Saturn once migrated inward and then outward again, scattering smaller bodies and shaping the distribution of asteroids and comets. This grand tack hypothesis suggests that the harmony we see today emerged from turbulence, much like a symphony that begins with dissonance before settling into melody. Even now, tiny shifts continue. Earth's orbit is influenced by the gravitational tug of other planets, leading to cycles known as Milankovitch cycles that affect climate over tens of thousands of years. These cycles help explain the timing of ice ages, showing how the solar system's harmony directly shapes life on our planet. Think about this. The solar system is vast. Neptune orbits nearly 30 times farther from the Sun than Earth, and the Oort cloud, a distant shell of icy bodies, may extend 100,000 times farther still. Yet across this immensity, the same rules apply. From the innermost orbit of Mercury to the outermost reaches of comets, gravity and motion weave a single tapestry. History reminds us how revolutionary this discovery was. For millennia, humans saw the heavens as unpredictable, governed by divine will or chance. But when astronomers uncovered the mathematics of motion, they revealed that the universe was not arbitrary but ordered. The solar system became a cosmic clock, its gears turning in precise, predictable ways. This realization not only advanced science, but also reshaped philosophy, showing that nature followed laws that the human mind could comprehend. And yet, even in its harmony, the solar system holds surprises. Chaotic dynamics lurk in certain regions, where small changes can lead to unpredictable outcomes. The orbit of Mercury, for example, shifts subtly due to the influence of general relativity, Einstein's refinement of Newton's gravity over immense timescales. Even tiny instabilities can cascade, potentially ejecting bodies or causing collisions. Harmony and chaos, it seems, are partners in this cosmic dance. Today, we use this understanding in practical ways. Space agencies design missions that exploit orbital mechanics, slingshotting spacecraft around planets to gain speed with minimal fuel. The Voyager probes, for example, used a rare alignment of the outer planets in the 1970s to tour the solar system, riding the currents of gravity like surfers catching waves. These missions remind us that the hidden harmony of the solar system isn't just theory, it's a tool for exploration. But perhaps the most humbling part of this harmony is how it connects to life itself. Earth orbits in what we call the habitable zone, the region where liquid water can exist. Our moon stabilizes our tilt. Jupiter's immense gravity acts like a shield, deflecting many comets and asteroids that might otherwise bombard Earth. Each piece of the solar system plays its part in creating the fragile conditions that allow us to exist. So when we speak of the solar system's hidden harmony, we are speaking of more than mathematics. We are describing a cosmic symphony in which every planet, moon, and particle has a role. It is a balance between order and chaos, between stability and change, that has unfolded over billions of years. And here's the wonder. From our small vantage point on Earth, we have not only noticed this harmony, but deciphered its rules. We can predict eclipses centuries in advance, calculate spacecraft trajectories with pinpoint accuracy, and trace the subtle patterns that connect our climate to the orbits of distant planets. The solar system is not just our home. It is a masterpiece of natural order, hidden in plain sight. Comets and asteroids, ancient cosmic travelers. Here's a fact that might surprise you. Long before telescopes or spacecraft, humans already knew of comets. They appeared suddenly in the night sky, brilliant, ghostly streaks that seemed to defy the steady, predictable motions of the planets and stars. To ancient civilizations, these glowing wanderers were omens of change, sometimes feared as harbingers of disaster. Today we see them differently, as ancient messengers carrying the story of our solar system's birth. Asteroids and comets are often lumped together, but they are distinct. Asteroids are rocky remnants, primarily found in the asteroid belt between Mars and Jupiter. They are the leftover building blocks of the planets, rubble that never quite coalesced into a world. Comets, on the other hand, are icy bodies from the colder outer regions of the solar system. When they approach the Sun, heat transforms their frozen surfaces into glowing tails that can stretch for millions of kilometers. Both are small compared to planets, but both hold outsized importance for understanding our cosmic history. To see why, we need to go back to the early solar system. Around 4.6 billion years ago, the Sun ignited at the center of a swirling disk of dust and gas. From this disk, planets formed. But not all material was swept up. Some of it remained as planetesimals, small bodies that never grew larger. These fragments are time capsules, preserving the original chemistry of the solar system. Studying them is like opening a geological archive older than any rock on Earth. Asteroids reveal the rocky side of this history. Most are irregular in shape, scarred by craters from countless collisions. Some are metallic, rich in iron and nickel, while others are carbonaceous, containing organic compounds and water-bearing minerals. Missions like NASA's OSIRIS-REx, which visited the asteroid Bennu, are giving us direct samples to study. These pieces of rock and dust may help us understand not only how planets formed, but how life's ingredients arrived on Earth. Comets tell another part of the story. Rich in water, ice, and complex molecules, they may have delivered crucial materials to the early Earth. Some scientists suggest that much of our planet's water could have been brought by cometary impacts. Others argue that while comets contributed, asteroids likely played the bigger role. Either way, comets and asteroids are more than debris. They are couriers of life's potential. History shows how comets have fascinated us. Halley's Comet, perhaps the most famous, has been observed and recorded for millennia. In 1705, Edmund Halley used Newton's laws of motion to calculate its orbit and predicted its return every 76 years. When it reappeared in 1758, right on schedule, it was a triumph for science, a shift from superstition to understanding. Suddenly, comets were not omens, but predictable travelers, part of the solar system's great clockwork. Yet, these travelers are not harmless. Throughout Earth's history, asteroid and comet impacts have reshaped life itself. The most famous example is the Chicxulub impact. 66 million years ago, when a massive asteroid struck the Yucatan Peninsula, the impact unleashed energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a nuclear winter that darkened the skies. The result was the extinction of the non-avian dinosaurs, clearing the way for mammals, and eventually humans to thrive. Even smaller impacts can be devastating. In 1908, an asteroid exploded over Siberia, in what is now known as the Tunguska event, flattening 2,000 square kilometers of forest. In 2013, a meteor, just 20 meters wide, exploded in the atmosphere above Chelyabinsk, Russia, injuring over 1,000 people. These events remind us that Earth's place in the cosmos is not entirely safe, and that ancient travelers can still pose a threat. But we are no longer powerless. Today, scientists actively track near-Earth objects, mapping their orbits and predicting close approaches. In 2022, NASA tested a planetary defense strategy with the DART mission, deliberately crashing a spacecraft into an asteroid to alter its path. It was the first time humanity attempted to change the course of a celestial body, an astonishing step in becoming caretakers of our own planet's safety. Still, comets and asteroids are more than potential hazards. They inspire exploration and imagination. Space agencies dream of mining asteroids for rare metals, or harvesting water ice to support future colonies on the Moon or Mars. Science fiction envisions ships built from hollowed-out asteroids, carrying human pioneers into deep space. In these visions, the ancient travelers become stepping stones for our own cosmic journey. Think about it. These are objects older than Earth itself, wandering for billions of years in silence. Some have passed close to the sun countless times, shedding their tails like glowing signatures in the sky. Others have remained in deep freeze at the solar system's edge, untouched since the dawn of time. When one of them crosses our skies, we are seeing not just a spectacle, but a fragment of cosmic history, an emissary from the solar system's beginnings. And so, the next time you see news of a comet streaking past, or a meteor burning in the night sky, pause for a moment. These travelers are reminders that we live in a system that is ancient, dynamic, and deeply interconnected. They are both danger and gift, both relic and possibility. In their orbits, we see echoes of creation, and perhaps glimpses of our own future, as wanderers among the stars. The Oort cloud, the solar system's edge. Think about this. The solar system, as most of us imagine it, ends with Neptune, or maybe Pluto. Beyond that, it feels like empty space. But in reality, our sun's influence stretches far, far beyond the orbit of any planet. At the edge of this invisible frontier lies a mysterious sphere of icy bodies, the Oort cloud. It is a place we have never seen directly, yet it may hold more objects than all the planets combined. The Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. He noticed that some comets entering the inner solar system had orbits too distant and elongated to originate from the asteroid belt or Kuiper belt. Instead, they seemed to come from a vast reservoir much farther away. His hypothesis suggested that the Sun is surrounded by a shell of icy bodies extending perhaps 100,000 astronomical units, a distance so immense that light takes more than a year to cross it. To put that in perspective, Earth is 1 AU from the Sun. Neptune, the most distant planet, orbits at 30 AU. Voyager 1, the furthest human-made object, launched in 1977, has just recently crossed into interstellar space at around 160 AU. The Oort cloud, if it exists as we believe, begins perhaps 2000 AU from the Sun and stretches tens of thousands of AU farther still. In other words, it is so far away that even our fastest spacecraft would take tens of thousands of years to reach it. What might it look like? The Oort cloud is thought to be a diffuse sphere, with trillions of icy bodies orbiting in every direction. Unlike the Kuiper belt, which is a flat disk beyond Neptune, the Oort cloud is spherical, enveloping the solar system like a vast shell. These icy bodies are relics from the solar system's formation, material flung outward by the gravitational pushes of the giant planets. Some may even have originated around other stars, captured by the Sun's gravity during the solar system's early years. The Oort cloud is the birthplace of long-period comets, those that take thousands or even millions of years to complete an orbit. When disturbed by passing stars, galactic tides, or other gravitational nudges, an icy body from the Oort cloud can be nudged inward. It then falls toward the Sun, heating up and forming the glowing tails we see as comets. Every long-period comet that streaks across our skies is a visitor from this distant frontier, a messenger from the solar system's edge. But here's where it gets even more interesting. The Oort cloud marks the boundary between the Sun's gravitational domain and the broader galaxy. Beyond it, the pull of the Sun weakens, and other stars and the Milky Way's tidal forces begin to dominate. In a sense, the Oort cloud is both part of our solar system and a threshold into interstellar space. It is the final outpost of the Sun's family, before the stars themselves take over. Though we cannot see the Oort cloud directly, indirect evidence supports its existence. The sheer number and variety of comets we observe suggest a massive, distant reservoir. Simulations of solar system formation also predict such a structure, explaining how icy bodies were scattered outward by Jupiter and Saturn in the solar system's youth. It is one of those fascinating cases where absence of direct proof is balanced by the weight of overwhelming indirect clues. The Oort cloud also raises philosophical questions about boundaries. Where does the solar system truly end? Is it at Neptune, at the Kuiper belt, at the Oort cloud's edge, or at the heliopause, the boundary where the solar wind gives way to the interstellar medium? Each definition has merit, but the Oort cloud reminds us that the solar system is far larger and stranger than the tidy diagrams in textbooks. One day, we may see it more directly. Future generations of telescopes or deep space missions might detect Oort cloud objects, giving us our first real glimpse of this elusive realm. Imagine a spacecraft sent to rendezvous with an Oort cloud body, studying material unchanged for billions of years. It would be like opening a time capsule from the dawn of the solar system. Until then, the Oort cloud remains a frontier of imagination. It is a silent sphere of icy wanderers, each one drifting slowly in the dark, waiting for the rare moment when gravity nudges it inward. Some of those wanderers have already visited us as comets, igniting wonder and curiosity in human observers for centuries. Others will return long after our own civilization is gone, still tracing their timeless orbits around the distant Sun. So the next time you look at a comet blazing in the night sky, think of the Oort cloud. That glowing traveler began its journey in a realm so distant and mysterious that we can scarcely fathom it. It is a reminder that the solar system does not end where our maps often stop. Instead, it stretches outward into a frozen halo, connecting us not just to the planets we know, but to the very edge of the sun's domain. The Oort cloud is the solar system's frontier, not an ending, but a threshold. Beyond it lies the galaxy itself, and the promise that we are part of something even larger than the sun's embrace. Our Milky Way, a galactic home of stars. Here's a fact that might surprise you. When you look up on a clear night and see the hazy band of the Milky Way stretching across the sky, you are looking not outward into the infinite, but inward, across the disk of our own galaxy. That faint glow is the combined light of hundreds of billions of stars, woven together into a sprawling cosmic city that we call home. The Milky Way is vast. It is a barred spiral galaxy about 100,000 light-years across. To put that in perspective, if the sun were the size of a grain of sand, the Milky Way would stretch the length of the continental United States. Within it are perhaps 200 to 400 billion stars, billions of planets, and untold numbers of clouds, clusters, and nebulae. And yet, for all its enormity, we are only just beginning to map its true structure. Our galaxy is shaped like a disk, with graceful spiral arms winding outward from a central bar-shaped bulge. The sun sits about 2/3 of the way out, roughly 27,000 light-years from the galactic center. From our vantage point, dust clouds obscure much of the view, making the Milky Way both a familiar sight and a mystery. It's as if we are inhabitants of a vast city, yet able to see only a few blocks around us. The stars in the Milky Way are not evenly spread. They gather into structures, each with its own character. The thin disk, where the sun resides, is rich in young stars, gas, and dust, the raw material for star formation. The thick disk, extending above and below, contains older, dimmer stars. At the heart of the galaxy lies a dense bulge of stars, and beyond the disk is the stellar halo, a spherical region populated by ancient globular clusters. But perhaps the most humbling feature of the Milky Way is its motion. Every star, including the sun, orbits the galactic center under the pull of gravity. Our solar system takes about 225 million years to complete a single orbit. A galactic year. That means the last time the sun was in this position, dinosaurs were just beginning to walk the Earth. In a sense, our planet is not only orbiting the sun, but also drifting through the vast currents of the galaxy itself. Historically, humanity's understanding of the Milky Way has been a story of gradual revelation. For centuries, people thought the Milky Way was a band of glowing mist. In the early 1600s, Galileo's telescope revealed it was made of countless stars. In the 20th century, astronomers like Edwin Hubble showed that the Milky Way was just one galaxy among billions. Each discovery expanded our sense of scale, pushing us farther from the notion of being at the center of things. And yet, the Milky Way is not just vast, it is alive with activity. Star-forming regions within the spiral arms act as nurseries, giving birth to new suns and planets. Supernovae erupt, enriching the interstellar medium with heavy elements. Black holes lurk, invisible but powerful, bending space and time. The galaxy is a dynamic ecosystem, recycling material, shaping stars, and setting the stage for worlds like ours to exist. The Milky Way also reminds us of our connection to the wider cosmos. It belongs to the Local Group, a small cluster of galaxies that includes Andromeda and dozens of smaller companions. Together, these galaxies are part of an even larger structure, the Virgo supercluster, which itself is just one thread in the cosmic web that spans the observable universe. Our galaxy is not an isolated island, but one node in a grand cosmic network. Yet for all its grandeur, the Milky Way is deeply personal. Every atom in your body was forged within stars scattered across this galaxy. Every photon of sunlight began in the heart of a star, 27,000 light-years from the galactic center. When you gaze at the Milky Way, you are seeing not just stars, but your own origins written in light. And the Milky Way has its own destiny. In about 4 billion years, it will collide with the Andromeda galaxy. Far from a violent smash, this merger will be a slow, graceful dance lasting billions of years. reshaping both galaxies into a new, larger one. Often dubbed Milky Way, the stars themselves are unlikely to collide. Space is too vast, but the gravitational interactions will trigger new waves of star formation. Our Sun, if it still shines, will find itself in a galaxy very different from the one we know today. The Milky Way is both home and horizon. It is the environment that nurtured our solar system, the context for our existence, and the launching pad for our curiosity. To stand under the night sky and see its glow is to feel both small and connected, a single observer in a galaxy of billions, yet also a product of that very system. So the next time you look at the Milky Way, remember this: you are not merely looking at stars, you are looking at your neighborhood, your birthplace, and your future. The galaxy is not just out there, it is within you, in the atoms of your bones, in the light that warms your skin, and in the story of life itself. The spiral arms and their hidden nurseries. At first glance, the spiral arms of the Milky Way look like decorative flourishes, sweeping curves of starlight winding gracefully around the galaxy. But they are far more than that. These arms are bustling avenues of activity, where stars are born, live, and die. They are nurseries of creation, hidden in clouds of dust and gas, shaping the future of the galaxy one star at a time. To understand them, we first need to rethink what spiral arms actually are. They are not rigid structures, like spokes in a wheel. Instead, they are density waves, regions where matter bunches up as it orbits the galactic center. Imagine cars on a highway during rush hour. Each car keeps moving, but traffic jams form where vehicles slow down and cluster together. The spiral arms work in much the same way. Stars and gas move through them, creating bright lanes of light. But the arms themselves are patterns, not permanent fixtures. Within these arms lie the galaxy's star-forming regions, giant molecular clouds. Vast collections of gas and dust collapse under gravity, fragmenting into clusters of newborn stars. Some are massive and short-lived, burning fiercely and illuminating their surroundings. Others are smaller and longer-lived, like our Sun. Together, these newborn stars give the spiral arms their brilliance, glowing against the dark backdrop of space. Perhaps the most famous of these stellar nurseries is the Orion Nebula, visible even to the naked eye as a fuzzy patch in the constellation Orion. Located just over 1,300 light-years away, it is part of the Orion arm of the Milky Way, the very arm our solar system inhabits. In the heart of the nebula, hot young stars blast radiation into the surrounding gas, sculpting it into breathtaking shapes. The Orion Nebula is just one example of countless hidden nurseries scattered along the arms. These nurseries don't just create stars, they also forge planets. Around young stars, disks of dust and gas gather, gradually sticking together to form worlds. Some become rocky planets like Earth, others gas giants like Jupiter, and still others icy bodies like comets. In this sense, the spiral arms are factories, not just of stars, but of entire planetary systems. Every world, every ocean, every mountain ridge begins in the dark clouds of these hidden nurseries. But spiral arms are not only sites of creation, they are also theaters of destruction. Massive stars born in these regions live fast and die young, exploding as supernovae within a few million years. These explosions scatter heavy elements like carbon, oxygen, and iron into the surrounding space, enriching the interstellar medium. This material then seeds the next generation of stars and planets. Without this cycle, the universe would be barren, lacking the building blocks of life. The spiral arms, therefore, are engines of recycling, cosmic workshops where matter is endlessly reshaped. From Earth, we cannot see the entire spiral structure of the Milky Way directly. Dust clouds block much of our view. Instead, astronomers map the arms by tracing radio signals from molecules like carbon monoxide, which reveal the locations of star-forming clouds. Surveys of stars and gas have shown that the Milky Way has a barred spiral structure with several major arms and smaller spurs. Our solar system resides in a minor feature called the Orion Spur, sandwiched between the larger Sagittarius and Perseus arms. Think about this. The Sun has orbited the galaxy more than 20 times since it formed, During that journey, it has drifted in and out of spiral arms, passing through regions of star formation and destruction. Some scientists suggest these passages may even influence life on Earth, as supernovae in nearby arms could alter our climate or trigger evolutionary shifts. In this way, the hidden nurseries of the spiral arms may have shaped the history of our own planet. History, too, reflects humanity's fascination with spirals, from the spiral carvings of ancient stone monuments to the swirling galaxies revealed by telescopes. We have long recognized the spiral as a symbol of growth, continuity, and mystery. The spiral arms of the Milky Way embody all of these, stretching across tens of thousands of light years, yet operating through the same simple physics that govern a whirlpool or a seashell. Modern astronomy continues to probe these regions with powerful instruments. Space telescopes like Hubble, Spitzer, and now James Webb have peered into the dusty wombs of star-forming clouds, revealing the earliest stages of stellar birth. They show us that stars are not born in isolation, but in clusters, shaped by gravity, turbulence, and radiation. Each nursery is a complex environment, a balance of forces that determines which stars survive and which fade before they fully ignite. And perhaps the most humbling realization is this: our own sun was once part of such a cluster, born in a stellar nursery billions of years ago. Over time, its sibling stars drifted away, scattered throughout the galaxy. Somewhere out there, countless stars share the same birthplace as our sun. Though we may never know which they are, the spiral arms, then, are not just abstract features. They are family trees, tracing the origins of stars and worlds like ours. So when you gaze up at the Milky Way and imagine those sweeping arms, remember what they represent. They are not static decorations, but living structures, rivers of stars and clouds where the galaxy breathes and renews itself. Within them, stars ignite, planets coalesce, and elements for life are forged. They are hidden nurseries, both beautiful and vital, weaving the ongoing story of our galactic home. The spiral arms remind us that creation is not a singular event, but a process that continues across the galaxy, shaping not only what we see in the night sky, but what we are made of. In their hidden nurseries, the universe is always beginning again. The supermassive black hole at the center. Think about this. At the very heart of our Milky Way lies an object so powerful, so extreme, that not even light can escape it. And yet, without it, our galaxy might not look the way it does today. This is Sagittarius A, a supermassive black hole, containing the mass of about 4 million suns, crammed into a space no larger than our solar system. For decades, its existence was only suspected. Astronomers noticed strange motions in the stars near the galactic center, as if they were being pulled by an invisible hand. In the 1990s, using powerful infrared telescopes, researchers tracked these stars in detail. They moved in tight, fast orbits, whipping around an unseen object at incredible speeds. The only possible explanation: a supermassive black hole. These painstaking measurements earned Andrea Ghez and Reinhard Genzel the Nobel Prize in Physics in 2020. But what exactly is a black hole? In simple terms, it is the collapsed core of a massive star, an object so dense that space and time themselves curve inward around it. For a stellar black hole, the mass might be 10 or 20 suns, but Sagittarius A is something different. Millions of solar masses. Such giants are thought to form not from single stars, but through the merging of smaller black holes, or by feeding on matter for billions of years. Despite their terrifying reputation, black holes are not cosmic vacuum cleaners, sucking up everything around them. Their gravity is immense, yes, but it follows the same laws as any other mass. A star orbiting far from Sagittarius A's size is just as stable as our sun is within the Milky Way. But closer in, the rules change. Gas clouds, stars, and even unlucky planets can be torn apart, their matter spiraling inward in a brilliant whirl of energy before vanishing beyond the event horizon. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. What we saw was not the black hole itself. It can never be seen, but the glowing ring of hot gas swirling around it. That blurry, orange halo was a triumph of human ingenuity. the result of linking radio telescopes across the globe to create a planet-sized observatory. For the first time, we glimpsed the shadow of the monster at our galaxy's heart. Black holes like Sagittarius A are not just exotic curiosities, they shape galaxies. Their immense gravity influences the orbits of stars near the center, while powerful jets of energy from infalling matter can regulate star formation on galactic scales. In a sense, the black hole is both destroyer and creator, balancing the growth of the Milky Way over billions of years. Culturally, the idea of a black hole has always captured the imagination. It's the ultimate paradox, a place where physics as we know it breaks down, where time and space collapse. Science fiction writers have imagined them as gateways to other universes, or as cosmic doomsday machines. The reality may be stranger still, tied to deep questions about quantum mechanics and the nature of reality itself. And yet, despite their mystery, black holes are part of the natural story of the cosmos. They are inevitable outcomes of gravity, written into the very fabric of how stars and galaxies evolve. To study them is to push against the limits of human knowledge, asking questions that stretch from the behavior of atoms to the fate of the universe. The stars orbiting Sagittarius A remind us of the scale of these forces. Some move so quickly that they complete an orbit in just a few decades, a blink of an eye on cosmic timescales. These stars, known as S-stars, provide natural laboratories for testing Einstein's theory of general relativity under the most extreme conditions. So far, relativity has passed every test, but each orbit observed brings us closer to uncovering something new. Looking ahead, future telescopes will sharpen our view of the galactic center, revealing the dynamics of gas and stars in unprecedented detail. We may even witness a star or gas cloud being consumed, watching in real time as matter spirals into oblivion. Each discovery adds a piece to the puzzle, deepening our understanding of both the Milky Way and the universe at large. So the next time you look at the night sky, remember that beneath the calm shimmer of stars lies a hidden force, a supermassive black hole, silent and invisible, yet shaping the destiny of an entire galaxy. Sagittarius A is not a distant curiosity, it is part of our story, the dark anchor at the center of our cosmic home. Neighboring galaxies, the Andromeda connection. Here's a fact that might surprise you. Our Milky Way is not drifting alone in the cosmos. Just beyond the veil of our stars lies another great spiral, the Andromeda galaxy, racing toward us at 110 kilometers per second. In about 4 billion years, the two galaxies will collide and merge into one colossal system. Far from being a distant curiosity, Andromeda is our cosmic neighbor and our future partner in an immense celestial dance. Andromeda, also known as M31, is the closest spiral galaxy to us, lying just 2.5 million light-years away. That sounds impossibly far, but in the grand scale of the universe, it's practically next door. On a dark night, far from city lights, you can even see it with the naked eye, as a faint smudge of light in the constellation Andromeda. What you are looking at in that moment is a trillion stars, an entire galaxy, whose light has traveled across the void for millions of years just to reach your eyes. For centuries, humans thought Andromeda was simply a nebula, a fuzzy cloud of gas within the Milky Way. It wasn't until the early 20th century that astronomer Edwin Hubble, observing stars in Andromeda through a powerful telescope, proved it was far beyond our galaxy. This discovery shattered the idea that the Milky Way was the entire universe. Suddenly, the cosmos became infinitely larger, filled with countless galaxies stretching to the edge of visibility. Andromeda is enormous, more massive than the Milky Way, with roughly twice as many stars. Its spiral arms sweep outward like cosmic whirlpools, filled with star clusters, nebulae, and interstellar dust. At its center, like our own, lies a supermassive black hole, anchoring the galaxy with its invisible gravity. Surrounding it are satellite galaxies, small companions much like the Magellanic Clouds that orbit the Milky Way. Together, Andromeda and the Milky Way form the two dominant members of the local group, a cluster of more than 50 galaxies bound by gravity. But what truly captures the imagination is the future collision. 4 billion years from now, Andromeda and the Milky Way will draw together, pulled by their mutual attraction. When galaxies collide, the stars themselves rarely crash into each other. space is simply too vast. Instead, their gravity reshapes everything. Stars will be flung into new orbits, vast clouds of gas will collide and ignite bursts of star formation, and the spiral arms of both galaxies will warp and distort in slow-motion chaos. Eventually, after billions of years, the two galaxies will merge into a single elliptical giant, often nicknamed Milkometa. To any beings alive at that time, whether human descendants or entirely new forms of life, the night sky will be breathtaking. Andromeda will loom larger and larger, filling the heavens with billions of stars until the two galaxies finally blend. It will be a night sky unlike anything imaginable today. This idea that galaxies grow and evolve through collisions is one of the great revelations of modern astronomy. Galaxies are not static islands, but dynamic, ever-changing systems. The Milky Way itself has absorbed smaller galaxies over its history, their remnants visible as streams of stars stretched across the sky. Andromeda has done the same, leaving behind faint shells and arcs that tell the story of past mergers. The universe is a place of constant change, where even galaxies have life cycles. Andromeda also offers us a chance to study ourselves. By observing its spiral arms, its star-forming regions, and its stellar populations, astronomers can compare it directly with the Milky Way. It is in many ways a mirror, another grand spiral shaped by the same forces of gravity, gas, and time. Every discovery about Andromeda deepens our understanding of the Milky Way's past and future. Consider, for example, the globular clusters scattered around Andromeda. These dense balls of ancient stars are fossils of the early universe, some more than 10 billion years old. By studying their orbits and compositions, astronomers piece together the history of how Andromeda assembled itself, much as archaeologists reconstruct civilizations from ruins. The same techniques applied to the Milky Way reveal striking parallels, suggesting that galaxies across the cosmos share a common story of birth, growth, and collision. Andromeda has also inspired the human imagination for centuries. In ancient times, its faint glow was linked to myths. The constellation Andromeda itself comes from Greek legend, the princess chained to a rock as a sacrifice to a sea monster. Today, Andromeda represents something different: perspective. It reminds us that the universe is not limited to our starry home, but extends outward in staggering complexity. Modern instruments allow us to study Andromeda in extraordinary detail. Radio telescopes map its cold gas, infrared observatories peer through its dust, and space telescopes like Hubble have resolved individual stars in its outer halo. Each wavelength reveals a new facet: sites of star birth, violent supernovae, or the quiet glow of old stellar populations. And with the upcoming generation of telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, our picture of Andromeda will only sharpen. Perhaps the most poetic aspect of the Andromeda connection is the thought that someone, somewhere in that galaxy, might be looking back at us. If intelligent life exists there, they would see the Milky Way in their night sky, glowing as we see them. Their astronomers might be mapping our spiral arms, speculating about our black hole, or predicting the same inevitable collision. Across millions of light years, two civilizations could be staring at each other's galaxies, wondering the same questions. And so Andromeda is more than a distant smudge of light. It is our sibling in the cosmos, our partner in a future merger, and our window into the grand processes that shape galaxies. Its story is not separate from ours. It is entwined, written in the shared gravity that will one day bind us into one. The next time you step under a dark sky and catch a glimpse of Andromeda, take a moment to reflect. You are seeing not only another galaxy, but a vision of destiny, a reminder that even on the largest scales, the universe is dynamic, alive, and connected. And in that connection, our story becomes part of something unimaginably larger. Star clusters and stellar families. Here's something worth pausing on. Stars are not loners by nature. Most are born in groups, siblings forged together from the same collapsing clouds of gas and dust. These groups, known as star clusters, are the stellar families of the universe, each with its own character and story. By studying them, astronomers can peer into the life cycles of stars, from their fiery beginnings to their quiet old age. There are two main types of clusters: open clusters and globular clusters. Each represents a different chapter in the galaxy's history. Open clusters are the younger, looser families of stars. They form within the spiral arms of galaxies, where cold gas clouds collapse into dozens or hundreds of newborn suns. The Pleiades, also known as the Seven Sisters, is one of the most famous examples, visible to the naked eye in the constellation Taurus. These hot blue stars are just about 100 million years old, mere infants compared to the Sun's 4.6 billion years. Open clusters are like cosmic nurseries, bustling with youthful energy. But these families are fleeting. Over time, the gravitational pull of the galaxy tugs them apart, scattering their members across the disk. Our own Sun is thought to have been born in an open cluster billions of years ago. Its siblings are long gone, drifting in distant orbits through the Milky Way. Somewhere out there, stars with the same chemical fingerprint as the Sun still shine. Lost family members we may one day identify. Globular clusters, on the other hand, are ancient. They are dense, spherical swarms of hundreds of thousands of stars, packed so tightly that in their cores the night sky would blaze with hundreds of suns. Globular clusters orbit the galaxy's halo, far from the spiral arms, and they are among the oldest objects in the universe, some more than 12 billion years old. They are living fossils, remnants of the early days of galaxy formation. The contrast between these two families is striking. Open clusters represent youth and impermanence, fragile groups destined to disperse. Globular clusters represent endurance and age, holding together for billions of years. Together, they paint a picture of the galaxy's history, from its turbulent beginnings to its ongoing renewal. Clusters are not just pretty gatherings of stars. They are scientific treasure troves, because their stars all form at roughly the same time and from the same material. Clusters serve as natural laboratories. By studying them, astronomers can test models of stellar evolution with extraordinary precision. If one star in a cluster is older or different, it stands out, allowing researchers to refine their understanding of how stars live and die. One particularly intriguing aspect is the role clusters play in shaping planetary systems. In dense environments, close encounters between stars can disrupt developing planets or fling them into interstellar space. Some rogue planets, wandering the galaxy without a parent star, may have been ejected from such crowded nurseries. At the same time, these environments may also foster unique conditions for planetary diversity. Clusters, then, are not just families of stars, but cradles for worlds. Globular clusters also raise fascinating questions about dark matter and galaxy formation. Their distribution around the Milky Way hints at the galaxy's assembly, perhaps through mergers with smaller systems. Some globular clusters may even be the remnants of dwarf galaxies, stripped of their stars and absorbed long ago. In this way, stellar families preserve the memory of cosmic events billions of years past. Culturally, clusters have inspired awe since ancient times. The Pleiades are referenced in myths from Greece to Japan, from Native American legends to Aboriginal Australian stories. Their appearance in the autumn sky marked the changing of seasons, guiding agricultural cycles and storytelling traditions. Even today, when we look up and recognize these tiny gatherings of light, we are sharing a human connection thousands of years old. Modern astronomy continues to unlock their secrets. The Hubble Space Telescope has peered into the cores of globular clusters, resolving stars packed closer than grains of sand on a beach. The James Webb Space Telescope, with its infrared vision, is revealing the birth of stars in open clusters, piercing through dust clouds that once hid their earliest stages. These observations not only deepen our understanding of stellar families, but also remind us of the vast scales of time and space they represent. And in a personal sense, clusters remind us of our own place in the universe. Just as stars are born in families and scattered, so too are humans, connected by shared origins and dispersed across the earth. Our sun's lost siblings may be light years away, but their atoms, like ours, are bound by the same cosmic story. So the next time you step outside and notice the delicate shimmer of the Pleiades or the faint glow of a globular cluster through a telescope, remember what you are seeing. These are not just stars, but families, siblings bound by birth, carrying within them the history of the galaxy. and the promise of new worlds. In their light, we glimpse both the fragility and the endurance of the cosmos. Open clusters dissolve into the galactic tide, while globular clusters endure like ancient monuments. Together, they tell us that nothing lasts forever, but nothing is ever truly lost either. Every star, every cluster, every family becomes part of the greater story of the Milky Way. Nebulae, the cradles of new stars. Here's a thought to begin with. When you look up at the night sky and see the twinkle of a star, you're gazing at the product of a vast hidden process. Stars are not born in the open, but in shrouded nurseries of gas and dust called nebulae. These immense clouds, often spanning dozens or even hundreds of light years, are the wombs of the universe, dark, cold, and quiet, until gravity stirs them into brilliance. Nebulae come in many forms. Some are diffuse and faint, barely detectable except through sensitive telescopes. Others blaze with color, lit up by the very stars they've helped create. Among the most iconic is the Orion Nebula, visible even without binoculars. At just over 1,300 light-years away, it is a stellar nursery in action. Within its glowing veil, clusters of young stars are forming, still cocooned in the material that gave them life. If you could hover inside, the sky would be alive with newborn suns, radiation carving the gas into vast cathedral-like structures. But nebulae are not just beautiful, they are essential. Without them, there would be no stars, no planets, no life. They are composed primarily of hydrogen, the most abundant element in the universe, with traces of helium and heavier elements forged in earlier generations of stars. Over millions of years, patches of these clouds cool and collapse under gravity. As they condense, they fragment into smaller clumps. Within each clump, density and temperature rise until nuclear fusion ignites. A star is born. This process is not gentle. Newborn stars often blast their surroundings with fierce stellar winds and radiation, tearing away the very clouds that sheltered them. In some cases, the violence triggers the collapse of nearby gas, sparking the birth of more stars. Nebulas are therefore sites of constant feedback, a cycle of creation and destruction, where one generation paves the way for the next. Not all nebulas are nurseries. Some are remnants, the ashes of stars long gone. Take the Crab Nebula, for instance, the expanding shell of gas left behind by a supernova explosion, witnessed on Earth in 1054 AD. Its filaments of glowing matter are the scattered remains of a massive star, enriched with heavy elements like carbon, oxygen, and iron. Over time, these materials mix with interstellar gas, seeding future nebulae with the ingredients for new stars and planets. In this sense, nebulae embody the cosmic cycle, death giving way to life, endlessly repeating. There are also planetary nebulae, named not because they form planets, but because their round shapes once resembled them through small telescopes. These delicate shells are created when dying sun-like stars shed their outer layers. The result is a glowing bubble of gas, lit from within by the fading stellar core. The Ring Nebula in Lyra is a classic example, a luminous halo that reminds us of the destiny awaiting our own sun, billions of years from now. If nebulae seem dreamlike in appearance, that is partly because of how we see them. In visible light, many appear colorful, glowing in reds, blues, and greens. These hues correspond to different elements: hydrogen, oxygen, sulfur, excited by nearby stars. In truth, our eyes would see only faint glimmers. It is through long exposure photography and specialized filters that the full artistry of nebula is revealed. Images from the Hubble Space Telescope, like the famous Pillars of Creation in the Eagle Nebula, have transformed them into icons of astronomy. But beyond the beauty lies profound science. Nebulae are laboratories for studying star formation, one of the most fundamental processes in the universe. By observing them in multiple wavelengths, infrared, radio, X-ray, astronomers can peel back layers of obscuring dust, track the motions of gas, and detect the earliest signs of protostars. Instruments like the James Webb Space Telescope are now peering deeper than ever, uncovering details hidden for billions of years. Our own sun once emerged from such a nebula, likely alongside hundreds of stellar siblings. Over time, the cluster dispersed, and the nebula itself dissolved into the interstellar medium. We will never know exactly which cloud bore our star, but we know the process continues across the galaxy. Every shining sun in the sky, every world circling it, began in the womb of a nebula. Culturally, nebulae occupy a special place in our imagination. They are symbols of mystery, transformation, and creation. Ancient observers could not see them in detail, but modern astronomy has turned them into cosmic artworks, reminding us of the scale and beauty of the universe. Their ghostly forms remind us that the cosmos is not static, but alive with processes both creative and destructive. And here's the humbling truth. Every atom in your body, carbon in your cells, oxygen in your lungs, calcium in your bones, was once forged in stars and spread into space through nebulae. When you breathe, when you move, you are living proof of the nebula's legacy. You are, in the most literal sense, stardust reassembled. So the next time you see an image of a nebula, don't just admire its beauty, see it as a mirror. Within those glowing clouds are the origins of stars, planets, and life itself. Nebulae are not just distant objects. They are the cradles of creation, the engines of cosmic renewal, and the ancestors of everything we know. Supernovae, the cosmic recycling process. Here's a dramatic fact. Every atom of iron in your blood was born in the heart of a dying star. Without supernovae, those titanic explosions that mark the death of massive suns, life as we know it would be impossible. These cataclysmic events may be violent beyond imagination, but they are also the great recyclers of the cosmos, seeding the universe with the raw materials for planets, oceans, and living beings. To understand supernovae, we must start with how stars live and die. A star spends most of its life fusing hydrogen into helium, balancing the inward pull of gravity with the outward pressure of radiation. For stars like our Sun, this process lasts billions of years. But when the fuel runs out, gravity wins. The core contracts, outer layers are expelled, and what remains is a white dwarf, a quiet, cooling ember. For massive stars, however, the ending is far less gentle. Stars more than 8 times the mass of the Sun burn through their fuel at a furious pace. They fuse heavier and heavier elements, carbon, oxygen, silicon, until they reach iron. And here the story shifts. Iron cannot produce energy through fusion. Instead, the star's core collapses in an instant. In less than a second, the outer layers rebound off the imploding core, triggering an explosion so bright it can outshine an entire galaxy. This is a core collapse supernova. The energy unleashed is staggering. In that moment, the star radiates more energy than our Sun will emit in its entire 10 billion year lifetime. Shock waves tear through the star's outer layers, scattering newly forged elements into space. Gold, uranium, calcium, oxygen. These heavy atoms are hurled across light years, mixing with interstellar gas. Over time, they enrich new generations of stars and planets. Without supernovae, the universe would be nothing but hydrogen and helium. But not all supernovae come from massive stars. Another type, called a Type 1a supernova, begins with a white dwarf in a binary system. As it steals material from its companion star, the white dwarf grows heavier until it passes a critical threshold. Then, in a runaway chain reaction, the entire star detonates in a thermonuclear explosion. These events are so consistent in brightness that astronomers use them as standard candles to measure distances across the cosmos. In fact, it was observations of Type 1a supernovae in the 1990s that revealed the universe's expansion is accelerating, a discovery that led to the concept of dark energy. Throughout history, supernovae have astonished skywatchers. In 1054 AD, Chinese and Arab astronomers recorded a guest star so bright it was visible in daylight for weeks. Today we know this was the supernova that created the Crab Nebula. In 1572, Tycho Brahe carefully documented another sudden star, challenging the ancient belief that the heavens were unchanging. In 1604, Johannes Kepler observed yet another, further cementing the reality of stellar death and rebirth. These sightings shaped astronomy, showing that the universe was dynamic, not eternal and fixed. Closer to our time, in 1987, astronomers witnessed supernova 1987A in the Large Magellanic Cloud. It became the closest observed supernova in centuries and provided invaluable data. For the first time, neutrinos, tiny particles released during the collapse, were detected on Earth, confirming theories of how such explosions unfold. That event remains one of the most studied in modern astronomy, a cosmic laboratory visible in real time. The role of supernova goes beyond recycling elements. They also sculpt galaxies. Their shock waves trigger the collapse of nearby gas clouds, sparking new rounds of star formation. In this way, they act as catalysts, linking the death of one generation to the birth of another. Too many supernovae can blow gas out of galaxies, stifling starbirth. Too few, and galaxies stagnate. It is a delicate balance, and supernovae sit at its heart. Supernova remnants, the expanding clouds left behind, are among the most spectacular sights in the sky. The Veil Nebula, with its delicate tendrils, is the wreckage of a star that died thousands of years ago. Cassiopeia, it glows with hot gas, revealing in X-rays the elements it cast off. These remnants are more than ruins. They are treasure chests, holding the ingredients of future worlds. And here is where the story becomes deeply personal. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in stars and spread by supernovae. You are, quite literally, made of star stuff, assembled from atoms that were once part of suns that lived and died billions of years ago. Each heartbeat is powered by cosmic recycling. Culturally, supernovae have inspired awe and fear. To ancient observers, the sudden appearance of a new star was often interpreted as an omen of disaster, of war, of change. Today, we see them as part of a natural cycle, destructive yet creative, violent yet necessary. They remind us that even in endings, there is renewal. Looking forward, astronomers eagerly await the next visible supernova in our galaxy. Statistically, one should occur every few centuries. Betelgeuse, the red supergiant in Orion, is a prime candidate. When it finally goes, whether tomorrow or 100,000 years from now, it will shine so brightly it could rival the moon. Humanity will once again watch the cosmos light up with the death of a star, and in that light, we'll see our own origins reflected. Supernovae, then, are not just astronomical events. They are the heartbeat of the universe, recycling matter, shaping galaxies, and writing the story of life in starlight. To witness one, even from afar, is to glimpse the cosmic forge at work. Dark matter, the invisible cosmic glue. At first glance, the universe seems straightforward. We look through telescopes, we see stars, galaxies, glowing nebula, and we assume that what we see is what exists. But here's the unsettling truth. The visible universe, all the suns and galaxies combined, accounts for less than 5% of reality. The rest is hidden, mysterious, and invisible. And much of it comes down to something we call dark matter, the unseen glue that holds the cosmos together. The idea first emerged not from imagination, but from frustration. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies. By measuring their motions, he realized something didn't add up. The galaxies were moving far too quickly to be held together by the visible matter alone. If only the stars and gas were present, the cluster should have flown apart. Zwicky proposed that some unseen mass, Dunkel Materie in German, was providing the extra gravity. His idea was radical, and at first few believed it. Decades later, in the 1970s, American astronomer Vera Rubin made a breakthrough. She studied the rotation curves of galaxies, the way stars orbit around their centers. According to Newtonian physics, stars farther from the center should orbit more slowly, just as planets in our solar system do. But Rubin found something astonishing. The stars at the edges of galaxies were moving just as fast as those near the core. It was as if some invisible halo of matter surrounded the galaxies, providing the necessary gravitational pull to keep them intact. This was compelling evidence that dark matter was real, and Rubin's work changed astronomy forever. So what exactly is dark matter? The simplest answer is, We don't know. It does not emit or absorb light, which is why we cannot see it directly. It doesn't interact with electromagnetic radiation in any detectable way, yet we know it must exist because we can measure its effects. It bends light through a phenomenon called gravitational lensing, where the path of light from distant galaxies is distorted by unseen mass. It shapes the large-scale structure of the universe, determining how galaxies form and cluster together. It is, quite literally, the scaffolding of the cosmos. One way to think of it is like the wind. You cannot see the wind itself, but you can see its effects on trees, waves, or clouds. Similarly, dark matter is invisible, but its gravitational fingerprints are everywhere. Without it, galaxies would not hold together. Without it, stars would scatter into space. Without it, the universe as we know it would simply not exist. Scientists have proposed many candidates for what dark matter might be. Some theories suggest exotic particles like WIMPs, weakly interacting, massive particles that barely interact with ordinary matter. Others propose axions, ultralight particles that could permeate space. More exotic ideas even consider entire populations of black holes or other unseen objects. Despite decades of experiments, from underground detectors buried in mines to particle colliders like the Large Hadron Collider, no direct detection has yet succeeded. The search continues, and each failure only deepens the mystery. Dark matter is not evenly spread throughout the universe. Instead, it forms vast halos around galaxies and clusters. Imagine an iceberg with only its tip visible above the water. The stars and gas we see are that visible tip, while the immense unseen bulk of dark matter lies hidden beneath. Computer simulations of galaxy formation show that without dark matter, galaxies would not have coalesced at all. It provided the gravitational framework in the early universe, guiding ordinary matter to condense into stars and planets. What's more, dark matter interacts with itself in subtle ways. Some evidence suggests it might not be completely inert, but could influence the shape and dynamics of galaxies. If confirmed, this would open an entirely new frontier in physics, hinting at forces beyond those we know. The mystery of dark matter is not just scientific, it is philosophical. For centuries, humans assumed that what we could see was the bulk of existence. But dark matter forces us to confront a universe where most of reality is hidden. We are living in a shadow play, where the luminous stars are only tracers of something much larger and more profound. Culturally, dark matter has captured our imagination. It appears in science fiction, novels, and films as a symbol of the unknown, the invisible forces shaping destiny. Yet in science, it remains stubbornly elusive. Every year, new experiments push the boundaries, hoping to glimpse a signal that confirms what dark matter truly is. Until then, it remains one of the greatest unsolved mysteries in physics. And here's the humbling conclusion. You, me, the Earth, the Sun, everything we call ordinary matter is just a small fraction of reality. The vast majority of the cosmos is built from something we cannot see or touch, something that holds the galaxies together yet slips through our detectors like ghosts. To study dark matter is to admit how little we truly know. In the end, dark matter is not just invisible glue, it is a reminder that the universe is deeper, stranger, and more mysterious than we can yet comprehend. And in that mystery lies both frustration and beauty. For as long as we look up at the night sky, we are chasing shadows, knowing that the unseen shapes everything we are. Dark energy, the mystery driving expansion. Here's a fact that might surprise you. Not only is the universe expanding, but that expansion is accelerating. Galaxies are rushing away from each other faster and faster, as though some invisible force is pushing the cosmos apart. This phenomenon, first confirmed in the late 20th century, stunned astronomers. The mysterious agent responsible for it was given a name, dark energy, and today it stands as perhaps the greatest enigma in all of science. To understand why this discovery was so shocking, we need to go back to Albert Einstein. In 1917, when he applied his theory of general relativity to the universe, he found something puzzling. According to his equations, the cosmos should either be expanding or contracting, but at the time, astronomers believed the universe was static. To reconcile the math with the accepted wisdom, Einstein introduced the cosmological constant, a kind of anti-gravity force that kept the universe in balance. Later, when Edwin Hubble revealed that galaxies were indeed receding from us, Einstein abandoned the constant, reportedly calling it his greatest blunder. For decades after, the prevailing view was that the universe's expansion, born from the Big Bang, should be slowing down under the pull of gravity. The question was whether it would slow to a stop, eventually collapse, or continue expanding forever. No one imagined it might be speeding up. Then came the late 1990s. Two independent teams of astronomers, using Type 1a supernovae as standard candles, measured the distances to far-off galaxies. To their astonishment, the data revealed that these galaxies were farther away than expected, meaning the expansion of the universe was accelerating. Something was counteracting gravity on the largest scales, pushing galaxies apart with ever-increasing speed. Dark energy was born as a concept. What is dark energy? That's the hard part. Unlike dark matter, which we at least suspect is made of particles, dark energy remains almost completely mysterious. The simplest explanation is that it could be Einstein's cosmological constant after all, a property of space itself. According to this idea, empty space isn't truly empty, but filled with a kind of vacuum energy that exerts repulsive pressure. The more space expands, the more of this energy there is, fueling further expansion in a self-reinforcing cycle. Other theories propose more exotic possibilities. Perhaps dark energy is a new kind of field, sometimes called quintessence, that changes over time. Or maybe our understanding of gravity itself is incomplete, and what we see as acceleration is actually the effect of new physics. Whatever the explanation, dark energy dominates the universe. It accounts for nearly 70% of the cosmic energy budget. By comparison, dark matter makes up about 25%, and ordinary matter, the stuff of stars, planets, and people, just 5%. To put it another way, everything we know, everything we can see, is a tiny minority. The rest of the universe is controlled by a mysterious energy we cannot detect directly. The implications are staggering. Dark energy doesn't just shape the present, it determines the future of the cosmos. If it remains constant, the universe will continue accelerating forever. Galaxies will drift farther and farther apart, until billions of years from now, only our local group remains visible. Stars will burn out, galaxies will fade, and the universe will grow dark and cold in a scenario known as the heat death. But if dark energy changes over time, other possibilities emerge. It could weaken, allowing gravity to slow expansion, and perhaps reverse it in a big crunch. Or it could grow stronger, tearing galaxies, stars, planets, and even atoms apart in a dramatic big rip. The fate of everything depends on a force we barely understand. Astronomers are working tirelessly to uncover its nature. Surveys of distant galaxies and cosmic microwave background radiation provide clues to how dark energy behaves across time. Projects like the Dark Energy Survey and the Euclid Space Telescope are mapping the universe in unprecedented detail, looking for subtle imprints of this mysterious force. Yet with every new dataset, the puzzle deepens. And here's the humbling truth. Dark energy is a name for our ignorance. It is a placeholder for something we cannot yet grasp. A reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. Culturally, dark energy has captured the human imagination as a symbol of the unknown. Writers and artists depict it as a cosmic current, a mysterious ocean upon which the universe drifts. For scientists, it is both tantalizing and frustrating. The most dominant component of reality, yet utterly elusive. Think about this. When you look at the night sky, the stars seem eternal and unchanging, but hidden in the fabric of space is a force that will ultimately decide their fate. Every galaxy, every star, every atom, everything we are, is caught in the grip of dark energy. In the end, dark energy reminds us that knowledge and mystery are two sides of the same coin. The more we learn about the cosmos, the more questions emerge. Perhaps one day, we will understand this invisible driver of expansion. Until then, it stands as the greatest riddle of existence, a silent force shaping the universe's destiny. The cosmic microwave background. Echo of the Big Bang. Imagine turning on an old television set. Not a sleek flat screen, but the kind with antennas. If you tuned it to an empty channel, you might remember the static that appeared. What most people never realized is that a tiny fraction of that static, about 1%, came from the oldest light in the universe, the cosmic microwave background, or CMB. This faint radiation is the afterglow of the Big Bang itself, an ancient whisper that has traveled across space for nearly 14 billion years. To appreciate why the CMB matters, we need to revisit the earliest moments of the cosmos. After the Big Bang, the universe was unimaginably hot and dense, a seething soup of particles, radiation, and energy. Photons, the particles of light, could not travel freely. They were constantly scattered by electrons in a plasma that filled all of space, making the early universe opaque, like the surface of a star. But about 380,000 years after the Big Bang, everything changed. The universe had cooled enough for protons and electrons to combine into neutral atoms in a process known as recombination. With fewer free electrons around, photons were suddenly free to travel unhindered. That first light has been journeying ever since, stretched into microwaves by the ongoing expansion of space. What we detect today as the CMB is quite literally the fossil light of creation. The discovery of this relic was a story of serendipity. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were testing a horn antenna in New Jersey. They were plagued by an unexplained background noise, persistent static that refused to go away no matter how carefully they adjusted the equipment. Unbeknownst to them, just across town, a team at Princeton University was preparing to search for exactly such a signal, predicted by Big Bang theory. When the two groups connected, it became clear. Penzias and Wilson had stumbled upon the echo of the universe's birth. Their discovery earned them the Nobel Prize and provided the strongest evidence yet for the Big Bang. At first glance, the CMB seems uniform, a nearly perfect background of microwave radiation filling the sky in every direction. But closer inspection reveals tiny fluctuations, temperature variations of just a few millionths of a degree. These faint patterns, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, are not random. They are the seeds of cosmic structure. Where the CMB was slightly denser, matter clumped together, eventually forming galaxies and clusters. Where it was slightly emptier, vast cosmic voids emerged. In this way, the CMB is a snapshot of the universe as an infant, showing us the blueprint from which everything we see today arose. By studying its fine details, astronomers can measure the universe's age, its composition, and even its geometry. Thanks to the CMB, we know the cosmos is 13.8 billion years old, made up of about 5% ordinary matter, 25% dark matter, and 70% dark energy. Without this ancient light, such precise knowledge would be impossible. The CMB also carries imprints of the earliest moments after the Big Bang. Some theories suggest that the universe underwent a brief but violent expansion known as cosmic inflation, magnifying tiny quantum fluctuations to cosmic scales. Evidence for this inflation may be encoded in the polarization of the CMB's light, subtle twists in its pattern that scientists are still searching for today. Detecting such signatures would open a window into physics at energies far beyond what we can achieve on Earth, offering clues about the very birth of space and time. What makes the CMB so remarkable is that it connects us directly to the origin of everything. Every microwave photon we detect today has traveled across the cosmos for billions of years, carrying with it a record of the universe's first chapter. It is a message from a time before stars, before galaxies, before even atoms as we know them. And yet this ancient signal is all around us, passing through us every moment of our lives. You don't need a telescope to be bathed in it. It is part of the fabric of the cosmos. Every second, trillions of CMB photons stream through your body, silent reminders of the fiery dawn from which the universe was born. Culturally, the CMB has reshaped our understanding of existence. Before its discovery, cosmology was a field of speculation, with competing theories about the universe's origin. The steady-state model, which proposed that the universe had no beginning, was still taken seriously, but the detection of the CMB dealt a decisive blow. The Big Bang was not just a theory. It had left behind a visible fingerprint written across the sky itself. The CMB is often called the afterglow of creation, but it is more than a poetic phrase. It is evidence that we live in a universe with a history, a beginning, and an evolution. It reminds us that the cosmos is not static but dynamic, a story unfolding over billions of years. And here's the humbling thought. When you gaze into the CMB, you are looking at the oldest light in the universe, the literal dawn of time. Beyond it, we cannot see, for no light could escape before that moment. It is, in a sense, the edge of the visible universe, the farthest horizon of human knowledge. The observable universe, what we can see. Think about this. When you look up at the night sky, you're not seeing the stars as they are right now, but as they were in the past. Light takes time to travel, and even the closest star beyond the sun shines at us from over 4 years ago. Now scale that idea outward. With the most powerful telescopes, astronomers can peer billions of light years into space, seeing galaxies as they existed not long after the Big Bang. This is the concept of the observable universe, the cosmic sphere of everything we can see, limited not by distance itself, but by time and the speed of light. At first glance, the phrase observable universe sounds straightforward, as though it's just a matter of how far our telescopes can reach. But in truth, it's a far deeper and stranger concept. The observable universe is defined by a cosmic horizon, the maximum distance from which light has had time to reach us since the birth of the universe. Given that the universe is 13.8 billion years old, you might assume this radius would be 13.8 billion light years. But because space itself has been expanding, the reality is far larger. The current observable universe extends about 46 billion light years in every direction, making it nearly 93 billion light years across. That's the limit of what we can see. Not because there's nothing beyond, but because light from farther regions simply hasn't had enough time to reach us. The true universe may stretch far beyond, perhaps even infinitely. What we observe is just a bubble, centered on Earth, though every observer anywhere in space would have their own observable bubble, centered on them. The scale is almost impossible to fathom. Within the observable universe, astronomers estimate there are around 2 trillion galaxies, each with hundreds of billions of stars. That means more stars than there are grains of sand on every beach on Earth. And surrounding those stars are untold numbers of planets, moons, and worlds, many of them still undiscovered. The sheer enormity defies comprehension, yet every bit of it is bound by the horizon of what light can reveal. But the observable universe is more than just a vast catalog of galaxies. It is also a time machine. The farther out we look, the farther back in time we peer. A galaxy seen 10 billion light years away shows us what it looked like 10 billion years ago. With telescopes like Hubble and James Webb, we are literally watching cosmic history unfold, tracing the growth of galaxies, the formation of stars, and the birth of elements across the ages. At the farthest reaches, we detect the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. Beyond that horizon, darkness reigns. Not because there is nothing there, but because light from that realm has not yet arrived. This horizon is sometimes called the cosmic light barrier. No matter how advanced our technology becomes, we can never see beyond it. The universe could be infinite, filled with uncountable galaxies beyond our reach, but they remain forever hidden. It's as though we live inside a bubble of visibility, watching shadows on its surface, while knowing the reality extends farther. And here lies a profound implication. The observable universe is not the same as the actual universe. We see only a fraction, and the rest, perhaps most of it, remains unknowable. Cosmology is thus an act of inference. By studying the patterns and laws within our observable sphere, we try to guess at the shape and nature of the cosmos beyond. Astronomers use the observable universe as a kind of laboratory. By mapping the distribution of galaxies across billions of light years, they can test theories of cosmic evolution. The large-scale structure of the universe, the filaments, clusters, and voids that span across unimaginable distances, offers clues about dark matter, dark energy, and the laws of physics themselves. Even the tiniest fluctuations in the cosmic microwave background help reveal the universe's contents and destiny. Culturally, the concept of the observable universe forces us to wrestle with humility. For most of history, humanity assumed the cosmos was small, perhaps limited to the stars we could see with the naked eye. Now we know that even with our most advanced tools, we glimpse only a bubble within a far greater whole. Beyond that horizon could lie wonders we cannot even imagine, galaxies stranger than any we've seen, or perhaps regions where the laws of physics play out differently. And yet, the observable universe is not static. As time goes on, more light from distant galaxies will reach us, expanding our horizon. But paradoxically, because of cosmic acceleration driven by dark energy, some galaxies are receding faster than light itself can bridge. They are slipping beyond reach, their light stretched into invisibility. In the far future, only our local cluster of galaxies will remain visible, and the wider universe will vanish from view. So the observable universe is not just a scientific boundary, it is also a window into the fleeting nature of knowledge. Right now, we live in a privileged cosmic era where the sky is filled with galaxies, where we can piece together the story of the cosmos, but billions of years from now, observers may see only darkness, unaware of the vast expanse that once lay beyond. The observable universe is, in the end, a cosmic diary. Each photon of light that arrives carries a page of history written billions of years ago. Together, they tell the story of how the universe grew from a fiery beginning into the vast tapestry we see today. It is a reminder that when we look outward, we are also looking backward, peering into time itself. And here's the humbling conclusion. Even with the most powerful telescopes, even with all our science, we can only glimpse a fraction of reality. Yet within that fraction lies enough wonder to keep us searching forever. The observable universe is both a boundary and an invitation to explore, to imagine, and to accept that the cosmos is always larger, older, and stranger than we can see. The multiverse, a possibility beyond imagination. Here's a mind-bending idea. What if the universe we see, the stars, galaxies, planets, and even ourselves, is just one of countless others? This is the concept of the multiverse, a hypothesis that stretches the limits of imagination and challenges our very understanding of reality. While it remains speculative, it arises naturally from some of the most successful theories in modern physics, suggesting that our cosmos may be just one bubble in a vast, perhaps infinite, cosmic foam. To understand the multiverse, we need to start with inflation, the rapid expansion of space that occurred in the first fractions of a second after the Big Bang. Inflation theory proposes that different regions of space could expand at slightly different rates. In some areas, inflation stops, forming pocket universes like our own, where matter clumps into stars and galaxies. In others, inflation continues indefinitely, creating new bubbles. Each bubble could have its own laws of physics, its own constants, and even its own dimensions of space and time. In this scenario, our universe is just one of many, perhaps countless realities, each isolated and inaccessible to the others. Another approach comes from quantum mechanics. In certain interpretations, every possible outcome of a quantum event is realized. But in a separate branch of reality, this many worlds view suggests an infinite number of parallel universes, where every decision, every random fluctuation, plays out somewhere. In one universe, you chose tea this morning, in another coffee. In another, perhaps humanity never existed. The implications are staggering. Every possibility that can happen does happen somewhere, in some version of reality. String theory, a leading candidate for a theory of everything, also hints at a multiverse. The mathematics of extra dimensions and multiple vacua suggest that the fundamental constants of nature, like the strength of gravity or the charge of the electron, could vary from one universe to another. In some universes, stars might never form. In others, life might arise in forms beyond imagination. The diversity is literally cosmic. If this sounds abstract, it's because it is. The multiverse is not something we can currently observe. By definition, other universes lie beyond our cosmic horizon, and light or information from them cannot reach us. Yet the concept has profound implications. It challenges the notion of uniqueness, the laws of physics, and the constants of nature that we often take for granted might be local features of our universe, not universal truths. And it offers a possible explanation for the so-called fine-tuning problem, the observation that our universe's parameters are precisely suited for life. In a multiverse of countless variations, it is perhaps not surprising that at least one universe, ours, allows stars, planets, and life to exist. Philosophically, the multiverse is both thrilling and unsettling. It forces us to reconsider our place in reality. Are we special, or just one of innumerable observers scattered across a vast ensemble of worlds? Does meaning arise from rarity, or is it something we create within our own universe? These are questions that blend physics with existential reflection. Despite its speculative nature, the multiverse has sparked intense scientific debate. Some researchers seek indirect evidence, such as anomalies in the cosmic microwave background, that might hint at collisions between our universe and another bubble. Others explore the theoretical consequences of inflation and quantum physics, testing whether the mathematics demands a multiverse. Even if direct proof remains elusive, thinking in multiversal terms helps physicists refine our understanding of fundamental laws. Culturally, the multiverse has seeped into science fiction, philosophy, and art. Stories of parallel realities, alternate histories, and infinite possibilities captivate the imagination because they resonate with a profound truth: reality may be far larger and stranger than any human mind can fully grasp. It's a concept that humbles, excites, and inspires curiosity all at once. And here's the poetic thought: in a multiverse, every choice, every event, every possibility exists somewhere. Somewhere, perhaps, another version of you is reading this script, thinking the exact same thing, or something wildly different. Somewhere, galaxies that never formed stars glimmer faintly in dark, alien skies. Somewhere, universes with entirely different physical laws swirl in eternal creation and destruction. In contemplating the multiverse, we confront the ultimate scale of existence. Our universe, vast though it is, may be just a single note in an infinite symphony. Yet even within this immensity, our experiences, our discoveries, and our understanding matter. They are the lens through which we glimpse the grandeur of reality. The multiverse is in the end an invitation to wonder. It challenges us to expand our thinking beyond the observable, to embrace mystery without fear, and to imagine that existence itself may be far more expansive than any telescope, any experiment, or any human mind can yet perceive. The fate of the cosmos. Endless expansion or collapse. Think about this. The universe is not static. From the moment of the Big Bang, it has been expanding, stretching the fabric of space itself. But how will this cosmic story end? Will the expansion continue forever, cooling and fading into darkness? Or will gravity one day win, collapsing the universe back into a singularity? The fate of the cosmos is one of the most profound questions in all of science, intertwining astronomy, physics, and philosophy. For much of the 20th century, scientists assumed the universe's expansion would gradually slow. Gravity, after all, exerts an attractive force, pulling galaxies toward each other. Early cosmologists considered three scenarios based on the density of matter in the universe. If density were high enough, gravity would eventually halt the expansion, leading to a big crunch, where all matter collapses back into an extremely hot, dense state. If the density were exactly critical, expansion would continue forever, but slow asymptotically toward zero. And if density were low, the universe would expand forever, with galaxies drifting apart into eternal isolation. This classical view, however, changed dramatically in the late 1990s with the discovery of dark energy. By observing distant Type 1a supernovae, astronomers found that not only is the universe expanding, but the rate of expansion is accelerating. Gravity is no longer the dominant player on cosmic scales. Dark energy is pushing galaxies apart, and it now appears that the universe's expansion may continue indefinitely. The simplest scenario is the heat death, also called the Big Freeze. As the universe expands, galaxies will recede beyond each other's visibility, stars will burn out, and black holes will slowly evaporate through Hawking radiation. Over trillions of years, the cosmos will become dark, cold, and desolate. Matter itself will thin out, and the universe will approach a state of maximum entropy, a uniform, lifeless expanse. Life as we know it would struggle to survive, and all energetic processes would cease. But the future could be stranger still. Some models suggest a big rip, where dark energy grows stronger over time. In this scenario, the expansion accelerates so violently that galaxies, stars, planets, and even atomic structures are torn apart. The universe would end, not in quiet stillness, but in an ultimate disassembly of all matter, leaving only empty space. The timeline for such a cataclysm is trillions of years, but the implications are profound. Even the fabric of reality could be stretched to its breaking point. Alternatively, a cosmic rebound remains a possibility, though less likely given current observations. If dark energy changes over time or loses influence, gravity might regain control. The universe could slow, stop, and eventually collapse in a big crunch. Some speculative theories suggest a cyclic model, where the universe oscillates through endless phases of expansion and contraction, perhaps giving rise to new Big Bangs. In this view, the cosmos has no absolute beginning or end, only an eternal rhythm of birth, death, and rebirth. The ultimate fate of the universe is also connected to the mysteries of quantum physics and the multiverse. Some hypotheses propose that vacuum decay or other exotic processes could alter the laws of physics themselves, triggering events we cannot currently predict. The end may be stranger than any of our current models can describe, a reminder that cosmic scales often exceed human intuition. Observing the universe today gives us clues about its future. By measuring the rate of expansion, the distribution of galaxies, and the behavior of dark energy, astronomers can refine models and narrow down possibilities. Satellites like Planck, WMAP, and future observatories continue to provide data, revealing the balance between matter, and dark energy. Even small anomalies in this balance could radically change our predictions for the universe's end. Yet while these cosmic scenarios unfold over trillions of years, far beyond any human timescale, their significance is philosophical as well as scientific. The fate of the cosmos forces us to confront impermanence on a universal scale. Everything we see today, galaxies, stars, planets, even life itself, is transient. We live in a fleeting epoch, a brief moment when the universe is luminous and dynamic. Understanding this fragility can inspire both humility and wonder. Culturally, ideas about the end of the universe have long captured human imagination. Ancient myths imagined cyclical worlds, cosmic floods, or fiery destructions. Modern science replaces myth with observation and theory, but the awe remains. Knowing that galaxies will one day vanish from view, that stars will fade, and that entropy will reign, gives a poignant perspective on our place in cosmic history. And here's a perspective to carry with you. The universe may be eternal in its expansion, or it may collapse in a final crunch, or it may rip itself apart. Whatever the outcome, life and consciousness are temporary sparks in the vast cosmic story. By studying the cosmos, we are participating in an ongoing narrative billions of years in the making, glimpsing both our origins and our eventual fate. Ultimately, the fate of the universe reminds us that the cosmos is dynamic, unpredictable, and astonishingly vast. Every star, every galaxy, every atom is part of a story that began with the Big Bang and will continue, whether through endless expansion, catastrophic rupture, or cyclical renewal, far beyond the reach of human lifetimes. It is a narrative that humbles, fascinates, and invites us to marvel at the grandeur of existence. Returning home, our place in the infinite. Hey guys, tonight we embark on a journey that begins billions of light years away, traverses the vast cosmic web, and ultimately returns to the small blue planet we call home. Imagine drifting past galaxies, witnessing the birth of stars and glowing nebulae, and feeling the silent pull of black holes at the heart of the Milky Way, all while contemplating the forces that govern the universe itself. This is a voyage through space and time, yet it circles back to Earth, reminding us that our planet, our sun, and our lives are intimately woven into the cosmos. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop your location and local time in the comments. I'd love to see where viewers are tuning in from as we explore the universe together. Returning home. To understand our place in the infinite, we must consider both scale and perspective. From Earth's surface, The universe seems vast yet tangible. We can chart the motions of planets, measure the orbit of the moon, and calculate the sun's influence. Yet these familiar orbits are but the smallest ripples in a vast cosmic ocean. The Milky Way alone contains over 100 billion stars, each potentially hosting planetary systems. Beyond it, billions of galaxies stretch across the observable universe, each a swirl of stars, gas, and dark matter. The enormity of it can be humbling, even disorienting. But even within this immensity, Earth holds a unique significance. It is a planet perfectly situated in the habitable zone of a stable star. It possesses liquid water, a protective magnetic field, and an atmosphere capable of supporting life. These conditions are rare in the universe, or at least, they appear to be. Every measurement, every exoplanet discovered, reinforces the delicate balance that allows life to flourish here. In a universe filled with extremes, blazing stars, black holes, frozen interstellar voids, Earth remains a fragile oasis, a rare stage where chemistry, energy, and time converge to create consciousness. Our solar system itself is a product of cosmic cycles. Every atom in our bodies was forged in stars, scattered by supernovae, and reassembled into planets. The rocks beneath our feet, the oceans, and the air we breathe are remnants of ancient stellar processes. In this sense, returning home is not just a matter of geography. It is a return to the very matter of the universe, a reunion with the long journey of stardust that began billions of years ago. Looking at Earth from space offers another perspective. Astronauts describe a profound sense of unity and fragility. The planet is a single delicate sphere suspended in the dark, surrounded by the void. Borders, nations, and divisions vanish from view, leaving only the interconnectedness of all life. This perspective reinforces a humbling truth. Though we are capable of exploring distant galaxies and theorizing about dark matter, our home remains the center of our experience, the cradle of our knowledge, and the foundation of our survival. The human quest to understand the universe mirrors this cosmic journey, from observing the motions of planets in ancient times to detecting the faint glow of the cosmic microwave background. We have pushed the boundaries of perception. Telescopes, satellites, and space probes extend our senses, allowing us to map the cosmos in unprecedented detail. And yet, no matter how far we reach, every discovery reflects back on our own place in the universe, shaping our understanding of who we are and why we exist. This return home also carries a philosophical dimension. Amid the enormity of the cosmos, our lives may seem fleeting, but in recognizing our place, we discover meaning. Earth is both small and extraordinary, a point of consciousness in a vast universe. Our curiosity, creativity, and exploration are extensions of the cosmic story itself. By studying the stars, we are learning about ourselves, our origins, our chemistry, our potential. The narrative of returning home is also a call to stewardship. As we explore distant worlds and study cosmic phenomena, we are reminded that Earth is the only planet we currently know to harbor life. Its protection, its preservation, becomes a responsibility framed by cosmic awareness. In the face of a universe of extremes, Earth is a rare and precious jewel. Caring for it is not just ethical. It is a reflection of our understanding of our place in the infinite. In the grand scheme, returning home does not diminish the vastness of the universe. Instead, it grounds our cosmic journey. The stars, galaxies, dark matter, and dark energy all converge into this single planet, this single vantage point. From here, we look outward and marvel, yet we also reflect inward, recognizing that our home is both a sanctuary and a gateway to understanding the infinite. So when you gaze at the night sky, know that you are seeing both the immensity of the universe and the reflection of your own origins. Every star, every galaxy, every particle of stardust carries the history of creation, and yet all of it is connected back to this one small world where life took root, where curiosity emerged, and where consciousness arose to contemplate the cosmos. Returning home is a reminder that while the universe is vast beyond imagination, our place within it is both significant and beautiful. We are the universe observing itself, a fleeting consciousness tracing the arc from the Big Bang to the stars and back to Earth. In understanding the cosmos, we understand ourselves, and in returning home, we carry the infinite within us, witnessing both the grandeur of space and the preciousness of our own world.